So in this tutorial session, we'll try to see the basics of transformer model and its insights, what motivation leads researchers to think about this model and build it, and how it was more useful than the earlier sequence-based models. And yeah, so we'll see about all the insights regarding the transform model and how it will be used for training on various data and used for sequence-to-sequence learning. So without taking much time, let's quickly go into that. I'm sharing my screen. Okay. So, as the transformer model was first presented with the title of this attention all is all you need, and these are the authors of the paper. So I thought that let's directly use their PPT and discuss with the example they provided in their presentation to understand what triggered to develop this model and what was the shortcoming of earlier models and approaches, which leads to develop of this beautiful model which worked so well for many of the AI tasks. So let's quickly revise. Yesterday, Ratnesh has already told you about this recurrent architecture, the RNNs, which learns sequence to sequence problem and tries to predict for a given input sequence to an output sequence. For example, suppose this that diagram shows a problem that it has to predict output sequence WXYZ based on the given input ABC. Okay, so what is happening here? There is a RNN layer, RNN model, which first of all encodes the given sequence of input, which is ABC. Okay, and after, so one by one sequential, because this is the sequential model, so it will starts with the first input A, process it, then in the next step take the input B, process it, and this way entire input sequence is processed one by one in sequential way. And for the generation output, like generation of the output sequence, it will start with a this tag, the symbol, the end of symbol, and which is used for both at the starting at the ending. People generally also use separate symbol like start symbol and end symbol, but suppose in this example the same tag is being used. So this tag is given as input, so it will generate the first symbol. In the next iteration, the first symbol will be the earlier generated output will be used for the next prediction X. This X will be used for the next generation in the output sequence Y. So in this way, entire output sequence WXYZ will be predicted. And remember that it is also using the encoded information of the given input. First, because we process all the input sequence through this RNN layer, and then use that encoded information to for the generation of output sequence. So here we can consider it as various problems, like we can use single RNN layer and do the encoding and decoding on the same model, same layer, or we can think of using two separate models. One model which used for encoding part, it will only take the input sequence as input and generate the input representation, which will be given as an input to the decoder model, and which will sequentially generate the entire output sequence as a separate model than the encoder model. So this is also people called encoder decoder architecture, where two separate models are used for, like, one encoder is used for processing input, which will generate a unified representation of the input, and which will be taken as input by the decoder to generate sequence generate sequential output. So this is the main agenda, main idea behind the sequence to sequence training. Let's quickly go ahead. So yes, as we have seen the encoder decoder architecture, people have tried to improve it with a attention mechanism. So first of all, the attention, which is the main big backbone of the transfer model, was actually encoded inside the encoder decoder architecture to improve the performance of sequence to sequence generation models. Okay. So what is happening, how attention works here, and how it improves the performance, let's try to understand with this diagram. So what is happening, the given input sequence, which is x1, x2, x3 up to xt. So there are t input elements, or we can say tokens, which will be processed in a bidirectional way. Okay. We can also use a unidirectional model, but suppose for the better representation of the input, we use the bidirectional model, and this bidirectional model actually process the input in both forward and backward way. Means each input in the sequence will have two representation. One is the forward representation and another one is the backward representation. They both will be concatenated and will represent the input sequence x3. So this is our encoder. And now we will not use the last representation, the representation of the last input in the sequence. Will not use that one for prediction. Yeah. So what instead, we apply the attention mechanism. And in attention mechanism, for the current generation, it checks like how much input should be taken from each and every element in the sequence, each and every input in the sequence. Okay, so this will attend each and every input, and how much it will attend, it is estimated by these probabilities, and these probabilities are nothing but the softmax of the dot product of the previous output which is there. It works as a query vector. This query vector will be multiplied with these representation of each input, and it will get some value, and applying softmax into that will get probabilities. And using the, or we can also say the weights, and using those weights they will tell how much particular input is to be attended for the current generation. So these probabilities, which are estimated by the softmax function, uh, is multiplied as a weighted of these representation with the previous output, and come. So this is the attention process, and after attention, the aggregation of all the input in this weighted way will give us one uh, vector, one unified vector. Okay, which is obtained through this aggregation of all the inputs with this attention mechanism. So that unified representation will now be used with the previous output to generate the current output in the sequence. Okay, so this is how it will be generating the entire output sequence. And the best thing is happening here is, for each generation, it will have different probabilities, okay, which is estimated through softmax function by applying the dot product of previous output and these representation. And these probabilities will decide the current generation, how the current generation, how much it should be influenced by each and every input. And that's actually the more natural logic. For example, suppose the machine translation, because for each word generation, when we do the translation manually, we generate two words. For generating the third word, we not only look at the two words which has been generated, but also we look at the source sentence again to see if there is any particular information that can be utilized for generating the third word in the output sequence. So every generation must look back the source sentence and get some useful information, and that is actually called the attention. And it is very beautifully applied in the transform model. And yeah, so there are many uh, importance, many things which have been incorporated in the transform model, which make it more efficient than the earlier uh, these sequencing models. Okay, so let's quickly see. There is one more drawback in this sequential prediction, sequential generation, is that the bottleneck problem is there for sure. Bottleneck means it has to process the entire sequence, input sequence, and only the last representation will have the information of all the sequences. There is a bottleneck at the last representation of the last this last input in the sequence. Other problem is if the input sequence is very large, then output sequence, which obviously be large, the large generation will has will have to attend so many nodes during the generation that it may lose some of the information which is long back in the sequence. Okay, so this is caused by vanishing gradient problem when there is long range dependency between an output word and input word. It may not be able, the information may not be able to flow properly or may get diminished during the generation. So that is also a major issue which has to be taken care of, and the transformer does that. Okay, so let's see the abstract way how the transformer is actually being utilized. Then we'll see more detail each and every aspect of it. So the transform model, as we know, you must have heard about it, applies multi-head attention. Don't worry about the term. This multi-head attention is the just an improved version of the attention that we have seen earlier. Okay, so here the attention being applied for the generation. The same mechanism is being used with an extension with a multi-head way of attending the input. We'll see in more detail. So what is happening here is that for the given input sequence, let's take the example of the machine translation. So it will generate the representation of each and every token in the input sequence in using this multi-head attention mechanism. And after getting the representation of each and every token in the input, it uses again decoder way of multi-head attention and applies it to generate the output sequence. Okay, and these multi-head attention, they are thought of in such a way, they are implemented in such a way they can be applied parallelly, and it saves a lot of time. So in place of processing each and every input one by one, it applies this attention together and get the representation of the input, and also use it for the generation in the same way. So, in summary, what we have observed from the earlier slides is that recurrent model sequential nature uh, forbid the parallelization, and because it has to process each and every term in the sequence one by one to generate the output, and it takes a sequential amount of time, means very long time for generating sequence in this way. The transform-based model applies the attention mechanism in a parallel way, so it completely avoid the recurrence for processing the given input. Okay. For example, in traditional machine translation, the attention mechanism was applied for learning dependencies between input and output. Okay. For example, just in the previous diagram here, for the given input sequence, although it is applying the attention mechanism, but still it has to process the sequence one by one, means it has to go by the sequential process one by one. But The transform model extend the same attention idea to apply first of all to the input, uh, to process the intra input information, means each word in the input sequence, how much it attends, uh, how much it depends on the other words in the input sequence. That's the intra input information processing. And also use the same criteria to generate the outputs sequence utilizing the intra output dependencies among all the words which has to be generated in the sequence. So because of this important point, the transform model has more better uh, capability than the earlier model, and they are faster, effective uh, to do this sequence to sequence generation. So that was a theoretical part. Let's see some graphical representation, how the transform model has been think of, what are various layers into it, and how the input is processed layer by layer. Okay, so this is the typical diagram given in the main paper, which consists of two parts, the encoder parts and the decoder part. And again, this encoder, so this one diagram, so this one part is one encoding layer. So likewise, there are an encoding layer then that you can think of. Okay, depending on the resources that you have, the amount of GPU which will be required to accommodate all those weights, you can define the number of n, means the number of the encoders into the entire encoder. So in the small, the general standard transform model, they have, I think, 8 or 12 input encoder, and same kind of. So you can just go to the word transform model and find out the configuration file, like how many encoders are there. So in one encoder, what is going on? Suppose we give an input sequence. We know that the transform model can take maximum 512 input sequences, including the start and end tag. And if the input is smaller, it is generally padded. And if the input is longer than the 512, the longer terms are truncated. So only the defined limit of words are taken as input, and those input uh, tokens are processed by input embedding layer, which will just transform each word into the embedding vector. Because those embeddings, they does not have they do not carry their order information, like particular word is occurring at which particular location in the sequence. That's why this criteria of summing up the positional encoding is necessary here. So that positional vector is added with each word embedding, and that summation is processed by encoder all the encoding layers and given to the decoding part. So after that processed vector, there are two main steps in each encoding layer, encoding process. One is apply the multi-head attention to extract the dependencies among the words, and after getting the word representation, after applying the multi-head attention, we have also apply feed forward layer. Okay, why the feed forward layer is important here? Because when you apply the multi-head attention and do some this addition and normalization. So yeah, before going to discussing about the feed forward, why it is important, so after multi-head attention, there will be some matrix multiplication and vector multiplication. uh, there may be chance, because of those multiplication, the value may jump up very high. Okay, and There may be some during the propagation, vanishing gradient problem can also be there. So first of all, there is a residual layer addition. Okay, means the same input is added to the output of multi-head attention. This is called the residual connection. Why it is important residual connection? Because during these processings, so many vector multiplication, the values may lose information or it become very similar. All the weights, all the values of the representation becomes very similar, and they lose the input diversity due to that vanishing gradient problem. So to avoid that problem, this uh, residual addition works well, and to, to maintain the diversity of the input throughout this process, because there's n number of inputs that are going to be applied. And after all this processing, some values may get rise very high, so all the values have to be normalized. So some normalization is very important here. So this is applied after each processing layer. Okay, so the every encoder has two processing layers like multi-attention and feed-forward layer, and afterwards it has to be residual adding and normalization required to be. Now let's talk about why the feed forward is being so important here. Because here what we are doing, just bunch of vector multiplication operation, and we know that vector multiplication just provide a transformation to a given word representation. Okay, it does not add any activation learning or any kind of activation into the input. Okay, so to apply non-linearity to the give to this processed output of multi-attention, we have to apply feed forward layer. So this feed forward layer is actually a dense layer consists of various sigmoid functions. So that which will process this output of multi-head attention to decide which information should flow further and which should not. Okay, so some non-linearity is applied here, and this provides the strength to this model of learning any non-linear criteria. Otherwise, it will just a kind of a transformation layer. That's it. So that's why every node will have these two processing layers, multi-attention and feed-forward. And I told you why residual addition and normalization is required. So that was the encoding node. The decoding node is also very same, but it has two multi-head attention. Okay, why two multi-head attention? Because one multi-head attention is required to be masked, because when we generate the third word in the sequence, it will use the two previous word. Okay, it will have the information, but it should not look upon the fourth or fifth or sixth word in the sequence. It should not look the future words in the sequence. So all the future words in the sequence has to be masked out. Okay, so that's why this masked multi-head attention is first applied on the output sequence during the generation of our output sequence. And after getting this masked multi-head attention, it will be used for multi-head attention, where uh, the query vector will be the output of masked multi-head attention, but the key and value vector will come from the encoding part, the last encoding node. Okay, and why this is important? Because the some information which is processed on the source input sequence will be transferred in this way. Okay, so the query vector will be using here in association with key and value vector, which is obtained from the encoder part, and then this multi-attention will be applied further in association with the same residual and normalization and the feed forward layer. So this is how the decoder layer, which is very similar to the encoder node. The only difference is first the masked multi-head attention is required to be applied so that it avoids looking at the future words, because it is not allowed. It's found to be kind of a cheating, uh, because when you do the generation, you only see the past words, not the future words. So I hope I'm able to make you understand about the inner part of the inner engineering of transformer model, what is happening in each and every node of whether it is encoder or decoder. Now let's see more closer way with some examples what operations being happening and how this idea of multi-head attention and QKV, the three vectors which are there to which actually leads to the application of this multi-headed attention into the problem. So the same thing, but in abstract way. What is happening? Suppose there is a translation problem. This is some input in one language, and it we want it to translate this sentence to English sentence. Okay? Suppose this is maybe French one only. So first, the French input is processed by various nodes of encoder. One, two, three, four, five, six. Okay, so six encoder node will process this input information, and this aggregated information will be used at each decoder node. Okay, so the decoder process will start with the very first decoding node. Then the same way the input will be processed, and one by one the entire output sequence will be generated. Now you can see that it has a more better way of processing the input information, keeping the better representation input. And because the attention mechanism is applied parallelly, each and every word representation can be done in no time. Okay, in just parallel way. So that make it more effective and useful for the sequence prediction task. So what are the basic ingredients in the encoder decoder architecture? In the encoder, it has first of all, it will take input embedding, do addition of positional encoding, then apply multi-head attention and feed forward with residual links. Okay, so this is what happening in the encoder part. In the decoder, the same. It will take output embedding as a input for generating the entire output sequence. Positional encoding is also required here. Multi-head attention with self attention, which is also mask multi-head attention, and then a multi-head encoder decoder attention, because it uses the encoder information with the decoder vector which is obtained from the masked multi-head attention, and then process it with the multi-head attention the same fashion, and applying feed forward with the residual. So the only extra thing is happening, we are applying the multi-head attention two times, one in a masked way and one in associated with the encoded information. Okay, and ultimately whatever output we get at the final decoding node, uh, it will be processed through linear layer, applied softmax, and the output probability. Just a minute. Okay, sorry for interruption. Let's continue. So yeah, we were just discussing about this inner part of the transform model, and so yes, quickly just revise what was happening in the encoder part. Encoder part was having self attention layer and a feed forward. Decoder was having self attention, then encoder, decoder attention, and feedback. So in each encoder and decoder, this is what is happening, and that's how uh, the information being processed and generated. Hopefully, I'm audible and properly visible. Yeah. Okay. So let's go ahead and find it up. So what is happening here? So yeah, let's discuss from the very scratch how the input is taken and processed by various layers. So each token, each word in the input, first of all, they are converted into word embedding and also the addition of the positional encoding. Then they will be processed by self attention, applying that multi-head attention that we talked about. And after getting that attention based output for each word, it will be given to feed forward layer. Okay, and feed forward will apply non-linearity, the very sigmoid function. And finally, the encoded version of the input word is obtained after this encoding node. So there will be n in such encoding nodes. The embedding size is actually flexible, you can set, but if you look at the example of transformer model, the BERT model, it has set 768 for each word embedding as a standard size, and it works for many examples in effective way. So self attention that we saw in RNN, calculating a hidden state allows an RNN to incorporate its representation of previous words vector it has processed with current one it's processing. Okay, so it means it uses the previous representation in the sequence to generate the current one. In the self attention mechanism, on the other hand, the transformer uses this idea where for the current word, it attend the, in all other words, all other neighboring words in the sequence parallelly. Okay, so in this way, for each word, the representation is generated independently from the other words. Okay, every word is attending to all other words in the sequence. That's why it is called self attention. So, in a diagrammatical way, we can understand it like this. Suppose we are processing 8 word and want to see this token, how it is attending to all other words in the sequence. Okay. So, that attention is actually obtained is done by multiplying various vectors which are there, like query k, query key, and value vectors. How that will be done we'll see, but by this diagram you can understand it. By that attention mechanism we will be able to know how much this token is related to the other token in the sequence. Okay, so it is more related to the animal, didn't t, not so much related to cross. Okay, because it was, so there are some terms which are very much closer to it, to which it is associated. So this way, each and every word will have an idea of attention and kind of attention, how much it is attending to each and every word, and it helps generating a representation for the given term in a more unique and dynamic way. And that representation plays very critical and very important role in many of the tasks, whether it is classification or generation or sequence prediction. So how this attention is being estimated and calculated, let's see with some examples. Okay, so there are certain steps into that. First step is for calculating the self attention. We, for each word, we require three vectors. Okay, those three vectors are query vector, key vector, and value vector. Query vector is a kind of, you can understand it. I'm asking something. I have this query, and there are a dictionary given, and which consists of key and value. So query will attend the key vector, okay, by dot product to identify how much a particular vector needs to be attended. Okay, so query and key will combinedly get that probability, the weight by which a particular word will be attended by the current word. So that's why these three vectors plays very important role here to identify the attention. The query key will find out the weight, and weighted aggregation of those value vectors will give us a more better representation, more better attention for the given word. So these vectors are created by multiplying embedding of a word with three matrices. Okay. So this is how it is happening. So suppose there are two words in the sequence, thinking and machines. So first we'll get the embedding of both the words x1 and x2. Then we already have a vector matrix, not vector matrix actually, matrix of weights for those many sequence. If suppose there are 512 tokens that can be taken as input, so this size of this matrix would be 500 cross the size that we have decided for each vector. Okay, and that actually decided by how many heads are there, how many what will be the multi-head criteria. Okay, so in some architecture you may want 12 heads. Okay, in some of the architecture you want to keep the number of heads smaller, okay, or very large number. So based on it, the size of each uh, query key value vector is decided, but ultimately the number of those will be fixed by the number of tokens is taken as input by the model. Okay, if there are 512 token taken, so the size of the number of rows would be 512. So this is query key and value vectors which will be multiplied with x to get the key value sorry, multiplied with this matrices to get the query key value vectors, and which will be used later for estimating the attention. So this is how the Q carry vector is utilized for finding out the attention for a given word. So first of all, Q and K are simply multiplied in to find out the dot product. So it will give us a number, and that number could be very high for some scenario. For the example, it could be smaller. So to normalize it, we'll divide it by the under root of the dimension of this vector. So this, in this way we'll get, and also apply the softmax in order to get the probability from between 0 to 1. So that probability is also, we can understand it as a weight, which will decide how much this particular word is related to the current word which we are processing currently. Okay, so that's why this input being processed, like if the qk vector, first of all they will be multiplied, then they will be scaled down by this number. Then if there is a masking during the training, you decide to mask some of the words in the sequence, so you apply, otherwise it is optional. And then apply the softmax to get the probability, and based on it, the ultimately do the matrix multiplication to get the final vector representation. So with example, let's try to see for the given in term, suppose thinking, we get the embedding, multiplying with the weight vectors, you will get the query key and values vectors. So first, in the next step, what is happening? We'll multiply QK. Suppose we get 112 for 112 for one head, 96 for another head. Okay, so we will apply. We'll first divide it to make it normalize, and then apply the soft mix. Okay, you can do the calculation, see whether the numbers are correct or not, but I'm sure they are. So ultimately, after applying the soft mix, you will find out that the current word uh, is dependent by this number 0.88 and dependent on machines by 0.12. So that's how you will find out like how much the weight should be given to a particular term in the sequence. And after that, both the vectors will be summed up, okay, by the weighted of the softmax probability, and we'll get at the end the attended representation for the given word. So we started with x1 and we got the attended representation for it as z1, and also for other word z2. So that's how this formula is being utilized for attended representation of the given input in the sequence. And this multi-head, because we are applying the q query vector through multiple divisions. Okay, we not apply only one q query vector. We divide the size of q query vector in a much smaller size. Okay, so why it is so useful? It expands the model's ability to focus on different positions or different perspective. Okay, one head maybe finding out or utilizing the dependency among the words, the part of speech dependency. Some of them may be finding out some other pattern into the input. So that's why having multiple heads uh, is give models ability to uh, process multiple patterns in the input. So for this example, suppose there are eight attention heads. So eight Q query vectors will be there for each word to process the dependencies or attention with all other words in the sequence. Okay, so that's how the attention is being defined, and with this concept we'll get different heads. So all for any word, like it is attending with animals, suppose. Okay, so because we are having eight heads, so there will be eight vectors, so ultimately they will be aggregated to sum up only one. But you can see the multi-head attention criteria is applied like this. So yeah, for the given word, uh, thinking and machines as an input, and we get certain vectors as an output. Okay, so z0, z1, and because there are we consider eight heads, so they will generate the vectors, and ultimately all of them will be concatenated and have a unified representation for the given input. Okay, so that's how uh, this information is processed. Okay, so first of all, these x is given as an input, processed by multiplied by various weight matrices to get the q carry vector, and then they will be multiplied with all other q query vectors to find out the attention representation for each input. Okay, and then they will be aggregated to find out the final attended representation of the given. So there were two words, so at the end you will also get two words representation, which carries the attended information on all other words in the input sequence. So that's how the multi-head attention criteria works, because it finds out the vectors by each and every head, okay, and then concatenate it to get the final represented information for particular one. So finally, yeah, residual connection. Although I told you what is why it is so important, but in this diagram you can understand it more clearly. That after applying the self attention, uh, we again add the input, okay, to maintain the diversity of the input, and it helps also avoiding the vanishing gradient problem uh, during the training. Okay, so the same thing what we already see for the input. Uh, it applies self-attention, then residual addition, normalization, feed forward, and then again residual addition and normalization. So, and based on number of encoding nodes, so those many times the encoding process will happen, and this input will be utilized in the decoder process, and they again there will be n number of decoding nodes, and that's how, because their inner engineering is like that, they have the capability to process as many as patterns that are there in the input. The only thing is now we have to provide it more data, okay, to train to actually grasp all possible patterns which are there in the input. If we have limited data, then these model may not be able to perform well because they have very limited knowledge based on the amount of data that you provide. So they, although their capability is higher, they have more weights to train on, and because of that they are also called data hungry models. Okay, same thing which we just discussed. So that was the final result that provided in that paper. Attention is all you need. So earlier models, they had applied different ensemble methods and attention mechanism on the traditional methods. So the complexity of the model was a lot, but the transformer model was simple, and they applied the same encoding node multiple times, and the base model was able to beat the all possible methods at that time. uh, and this was actually considered a breakthrough in this NLP domain to apply the transform model to solve many coming problems into that. Okay, so that was the thing we wanted to discuss. I think the last thing to talk about in this course. And so, if you have doubt in understanding any of the building blocks for the transform model, just let me know. I hope I'm able to discuss each and every part in more detail with examples what is happening. If any doubt remains, please ask. So, if no doubt, you can think of for the further in this the GAN course, the last thing will happen. There will be an exam starting at 5 o'clock. Okay, so everyone has to join online, and we'll be sharing a link of Google form, and there will be certain questions. uh, Everyone has to attend all those questions. Mostly will be MCQ questions, and you need to answer by just selecting the given option into the Google form, and you will be given 1 hour of time to attending all the questions, and participating in the exam is compulsory for everyone to get your certificates. Otherwise there will be issues or you may not be able to get your certificate. So please do participate into that. And yeah, we'll be giving you instructions properly just before starting the exam. So don't worry, if you will have any doubt and understanding, we'll be there to help you out. Any other confusion or doubt regarding the tutorial or the coming exam? Okay, so it's already uh, 4:23 around. Okay, so almost there 30 minutes. So we'll, let's meet again after 30 minutes and we'll start the exam at the exact time. It's 5 o'clock. See you there.